Okay, so first I want to thank Chun Chun for giving me the opportunity to speak today. And thanks to all the organizers for putting this conference together. So today I'm going to talk about 4D Gauss Bonnet theory from an amplitudes perspective. This is work done in collaboration with James Bonfacio and Kurt Hinterbichler. So recently there's been a lot of buzz and all these papers coming out about there possibly being a new theory of gravity in 4D coming from adding a Gauss Bonnet term to gravity. The recent interest in this idea was sparked by a paper by Glavin and Lin, where it was shown that when you added the Gauss Bonnet term with a coefficient of alpha over d minus 4, and then found some solutions and did some calculation, then if you took the d goes to 4 limit, there appeared to be additional contributions to your solutions. Okay, so yeah, this led to the idea that perhaps there is some alternative theory of a massless spin 2 particle with 2 degrees of freedom that had yet to be discovered. So Gauss Bonnet gravity comes from the family of Lovelock-Lanczos terms, which are the generalization of Einstein's theory in higher dimensions. Lovelock's theorem states that the most general theory of a single massless interacting graviton in arbitrary dimensions must come from a sum of these Lovelock-Lanczos terms, which take this form here. So in 4 dimensions, only L0 and L2 are non-trivial. And this corresponds to the cosmological constant in the Einstein-Hilbert term. The Gauss Bonnet term, which would correspond to L4, is topological in 4 dimensions and so doesn't contribute to the equations of motion. If a new theory of a massless graviton existed via taking this prescription, maybe it just doesn't have a standard Lagrangian and so could possibly avoid Lovelock's theorem. If this were true, it would be very exciting, as it would open up all sorts of new possibilities for non-Lagrangian theories, not only for gravity theories, but also for other topological theories like Galileans or something that are topological below some critical dimension. So we wanted to see, there's all these classical solutions being found, black hole solutions, but we wanted to see if this is happening, we should also be able to see it from an amplitudes perspective. And so even if there were no true purely gravitational 4D Lagrangian or equations of motion for this limiting theory, it doesn't necessarily mean it couldn't exist. Maybe this prescription just allows you to compute observables that would correspond to some new theory without a standard Lagrangian. And so we wanted to see what would happen if you try to use this prescription for scattering amplitudes. Okay. So we start by taking the d-dimensional Lagrangian for Gauss Bonnet theory, which just has your Einstein-Hilbert term and your Gauss Bonnet term, and then you expand around flat space, and you can then compute your Feynman rules. And so you'll get a propagator. The propagator doesn't receive any corrections from the Gauss Bonnet term in any dimension. Then you also get an Einstein-Hilbert cubic vertex. You'll get a cubic vertex coming from the Gauss Bonnet term. You'll get a quartic vertex from the Einstein-Hilbert term, and then you also get a quartic vertex coming from the Gauss Bonnet term. And this is all you then need to compute tree-level scattering amplitude for 4-point. Okay, so then that's what we did next. We put these pieces together. And so any tree-level scattering amplitude can be written in this form, where you have an exchange piece and a contact piece. And so then when we compute the scattering amplitudes, we expect to get something proportional or something with no alphas, which would correspond to just stuff coming purely from GR. You have an exchange diagram and a contact term. You would get something proportional to alpha, which would include an exchange between a GR vertex and then a Gauss Bonnet vertex, and then your Gauss Bonnet contact term, and then pieces proportional to alpha squared, which would come from an exchange diagram between 2 Gauss Bonnet terms. So to match the usual prescription, we would expect pieces going as alpha to be proportional to d minus 4, and then pieces going as alpha squared to be proportional to d minus 4 squared. So then that would allow us to make the usual replacement, which is taking alpha to alpha over d minus 4. Okay, so to take this d goes to 4 limit, we need to figure out how to do that. And so if we need to figure out what our polarization and momenta are going to look like. So one obvious choice is to just have the momenta and the polarizations lie in 4 dimensions. So you just have your momentum vector here, it only lies in the 4 dimensions, and then some polarization tensor where this is just your 4-dimensional tensor, and then all the other components are 0. And then it's obvious how to take this d goes to 4 limit. Okay, so we did that, and so these were the results. So the plus and minus here just corresponds to, in the 4-dimensional picture, the positive and negative helicity. But your amplitude and arbitrary dimension would look like this. And so these pieces just come from GR, they have no alphas. And then it turns out that the pieces proportional to 1 power of alpha just vanish. This is just due to kinematics. And then you get pieces going as alpha squared, but instead of them going like d minus 4 squared, they go like d minus 4. So if we were to make the usual replacement, the amplitudes would diverge and the d goes to 4 limit because we'd have 2 powers of d minus 4 on the bottom, so we'd cancel off one of the powers and then we'd have an extra one on the bottom. And so this would signify strong coupling. So if we want to get a finite contribution from the Gauss Bonnet term, we instead need to make this different replacement, which is alpha goes to alpha over square root of d minus 4. Okay, so if you make this replacement, where instead you take alpha to alpha tilde over square root of d minus 4 and then hold alpha tilde fixed, these will be the results. So you have your GR pieces, and then this is the contribution you get from that Gauss Bonnet term. And it turns out if you look at these closer, you'll see that the amplitudes you're getting are equivalent to ones coming from this Lagrangian here, where you have an Einstein-Hilbert piece, a scalar kinetic term, and then a coupling between Gauss Bonnet and a scalar. And so, yeah, the relevant vertices you get from this are your GR vertices, and then you also get this new scalar graviton-graviton vertex. And then from that you can build your 4-point amplitude, which includes these exchange pieces and contact term here. Okay, so yeah, this scalar theory is equivalent to what we got from the Gauss Bonnet term and taking the limit. Okay, so that was one choice for polarization and momenta choices. We can make another choice that looks like this. Then it's also obvious how to take the d goes to 4 limit with this choice. This would correspond to a scalar in the 4 dimensions because the transverse part doesn't pick out a preferred direction in extra dimensions. And so if you make this choice and plug that in for the different external legs and compute your scattering amplitude, you'll get something that looks like this here. And so the alpha piece here is going now as 1 over d minus 4, and so is the alpha squared piece. So to get a finite contribution from the Gauss Bonnet term, we need to instead make a different replacement. So now even another replacement, which goes as alpha to d minus 4 alpha. So if we make this replacement, then we'll get a finite contribution from the Gauss Bonnet term. Okay, so if you make that replacement and then take the limit, this will be your result. And this amplitude is equivalent to scalar scattering given by the d phi to the 4 Lagrangian, which has an Einstein-Hilbert piece, kinetic term, and then this d phi to the 4 piece. So the relevant cubic and quartic vertices look like this, and then the equivalent 4-point amplitude in 4 dimensions will look like this. Okay, so It seems like kind of strange that we're getting, you know, depending on what polarization we choose, we're getting all these different limits. And it seems like there should be some overarching theory or something that combines all these. And indeed there is. You can understand these results by dimensional reduction. So if you take your Gauss Bonnet theory, Einstein-Hilbert plus Gauss Bonnet term in arbitrary dimension, and then do a dimensional reduction. So we have now d equals 4 plus n, where we have n extra dimensions. We can write an ansatz metric like this, where we have a 4-dimensional metric. We have a scalar field which modulates the size of the extra dimensions. And then this dy is a flat n-dimensional manifold describing the extra dimensions. And then we set all the other Kluser-Klein modes to 0. If you use this and then integrate over the extra dimensions, and then if you perform a conformal transformation, you'll find this Lagrangian here. And so there's an Einstein-Hilbert piece, there's a coupling between Gauss Bonnet and a scalar field. We have a kinetic term, scalar kinetic term, and we also have scalar self-interaction terms. And if we set into 0, like we expect, we would get all this stuff would vanish. The Gauss Bonnet term would become topological, and then we just have Einstein-Hilbert term. We can also just view this Lagrangian, instead of viewing it as something that came from dimensional reduction, is now just a 4D Lagrangian with some parameter n. And so if we want to take the d goes to 4 limit, that's equivalent to taking the n to 0 limit. Okay, so we take that Lagrangian and then do the usual replacement. So this one's equivalent to the alpha goes to alpha over d minus 4, and then we take n to 0. We'll get this Lagrangian here. So we still have a scalar degree of freedom, but the kinetic term has vanished. And this indicates that the scalar field is infinitely strongly coupled. Okay, so to keep the scalar kinetic term, we need to canonically normalize. And so if we do that, and then we make that other replacement that we were finding, which is alpha over square root of n, and then take the n goes to 0 limit, our scalar self-interactions would diverge, but if we just ignore those, then we'll get this Lagrangian here. And this is the same one we were finding when doing the graviton scattering. But this one is also infinitely strongly coupled because of those scalar terms that are diverging. Okay, and then if we make that third replacement that we found, which is alpha goes to n alpha, and take the n to 0 limit, we get this Lagrangian here. And this is that d phi to the 4 Lagrangian. And this is the only non-trivial scalar tensor one that is not infinitely strongly coupled around flat space. Okay, so you still might say that, well, maybe you know, this procedure we're doing just isn't general enough, and there could still be some kind of other amplitudes that would correspond to a massless spin 2 that we just haven't found. But it turns out you can show using on-shell methods that there can't be any new 4-point amplitudes for a massless graviton that satisfy Lorentz invariance, locality, and unitarity without, you know, this limit somehow giving you extra derivatives or something. So to show this, we start by considering 4-point tree amplitudes, which in general dimensions. And so your amplitude will come in this form, which will be exchange terms plus contact terms. The exchange terms will have simple poles with residues that factor into products of on-shell 3-point amplitudes. And the contact terms need to be analytic and momenta and polarizations. So the Gauss Bonnet term comes with 4 derivatives. So an exchange diagram coming from some kind of dimensional continuation can have up to 6 derivatives. Here is a list of all the possible cubic vertices with 6 derivatives or less that obey conservation laws and are invariant under permutations of the particles. So you can only get these 3, and they happen to correspond to the Einstein-Hilbert piece, the Gauss Bonnet piece, and the R cubed piece. But an exchange diagram involving two of these vertices would contain 10 derivatives, and so this is too many. So this leaves us with cubic vertices only coming from GR and Gauss Bonnet. So if we were to take a linear combination of these and compute exchange diagrams, we would get one with a GR-GR vertex that would have 2 derivatives, another term with a GR and a GB vertex that would give 4 derivatives, and then a GB and a GB vertex, which would give 6 derivatives. And then we can write an ansatz for the contact term with up to 6 derivatives. So our contact term could have something with 2 derivatives, something with 4 derivatives, and then something with 6 derivatives. So the 2 derivative and 4 derivative contact pieces are uniquely fixed by requiring that the gauge invariance of the contact term is equal to negative the gauge invariance of the exchange term. But this doesn't uniquely fix the 6 derivative contact piece, which leaves 1 free parameter. But there is an additional contact term you can add with 6 derivatives, but this just corresponds to the Lovelock interaction of order R cubed, which vanishes in 4D. So if we take everything, this exchange diagram completely fixes this one by gauge invariance. This one fixes this one by gauge invariance. We still have one available term, but this just turns out to be a Lovelock interaction. And so if we take all this into account and then we reduce to 4 dimensions, the Lovelock terms all vanish except GR, and so in 4 dimensions we just get back GR. So there are no new gravitational amplitudes unless the limit that you take somehow adds more derivatives or spoils Lorentz invariance or unitarity or locality. So to summarize, when computing the graviton-graviton scattering amplitude in the Gauss Bonnet theory, and then taking the D4 limit, we found a different replacement was needed than the usual one, which went as alpha over square root of D minus 4. The resulting amplitude contained an extra scalar degree of freedom, and all these different limits can be understood by taking a Kaluza-Klein reduction and then taking the limit as the number of extra dimensions goes to 0. And so if you just scale and in different ways, then you'll get all the various scalar tensor theories that we were finding. Unfortunately, we do not find a new purely gravitational theory describing a massless spin 2 particle that evades Lovelock's theorem, but instead just find an extra scalar degree of freedom lurking around. So, yeah, that's all I wanted to say, and thank you guys for listening.
Well, thank you very much. I think it's fair now to have some questions to ask. Junshin, I think you have been the first to raise your hand, please.
Okay. I have a question. Since there's a discontinuity here with this limit D24 and this with the amplitude with D exactly equals to 4. This discontinuity just remind me that in the case of Proctor theory, if we take the mass of a photon to be 0, and still there's some kind of a similar discontinuity here, because in the case of Proctor theory, when you take the mass of a photon to be 0, and then you actually have a strong coupling in this longitudinal mode. But meanwhile, this strong coupled longitudinal mode is completely decoupled from the rest of part of the world, and then we can just ignore. No matter what happened in this longitudinal mode, it just doesn't matter anymore. And that is the way we smoothly connect Proctor theory to Maxwell theory in this massless limit. So in this Gauss Bonnet case, it seems there's a similar discontinuity between D24 limit and D equals to 4 exactly. So I'm wondering, do we have a similar prescription here, analog to this Proctor theory? Am I explain clearly?
Yeah. So it does seem kind of similar. Yeah, you get, though it didn't seem like the scalar field in this case fully decouples from the tensor modes here. So it seems sort of like when you take, like if you you can also do this with massive gravity, and if you take the m goes to 0 limit, then the tensor and the scalar mode don't completely decouple. And so you still have extra degrees of freedom. And so I think this is more like that case.
Okay, I see. I get your point. Is the discontinuity here is more similar to the one in massive gravity rather than the Proctor theory.
Yeah, I think so. Yeah.
I see. Okay, I get your point. Okay, thank you.
May I ask the question to? I have somehow I'm not an expert in this, but there is some. My idea is that somehow in this Gauss Bonnet, you have this factor d-4 sort of appearing in a natural way. So does it mean that if you would go with your expansion in this first case, if you would go to order in alpha, would it diverge with this kind of scaling, like alpha over square root of d-4?
So let me see if I didn't, you were breaking up a little bit, so I didn't fully hear everything. Were you asking if when you take, let me see,
Suppose you would go to terms higher in alpha than just alpha squared.
Oh, you mean like if you allowed for extra?
So alpha to the third or alpha 4.
Yeah, so if you went to higher, like 5 point, so in 4-point amplitudes, it stops at alpha squared. But if you computed higher point amplitudes, like 5-point or something, then you would get alpha cubed terms.
My question is that they would probably also have this d-4 factor coming from Gauss Bonnet. Wouldn't it be a problem with the scaling?
Let's see. I'm guessing they would, because yeah, we expect it to match what's coming from this Lagrangian here. So I would expect the scaling to work out so that you needed to make the same replacement when you included higher point, but I haven't done that calculation to know for sure, but I would expect it to just match whatever is coming from this Lagrangian here. If you start to, though, include like things with multiple scalars or something, or loop diagrams, then because this is strongly coupled, you might run into other interactions where it would diverge. So yeah, it could diverge when you look at higher order stuff, because there is some strong coupling going on.
Okay, thank you. There is another question.
Yep.
Yes.
Yeah, this morning we heard about an approach to this theory using in a Lorentz violating setting, in a setting where only space rotations are preserved. Did you think about considering Lorentz situations with Lorentz violation? Do you think you get something new then?
Yeah, we didn't consider that. You might get something new, and that's just something I haven't thought about. I really wanted to watch that talk this morning, but it was at 4 a.m. my time, so a little late. Hopefully I can watch the recording.
I have a quick comment on, I think for sure you'll get different amplitude, because if you look at this dispersion relation of tensor mode, even at the linear order level, already different. The dispersion relation is something like a k² plus k24. That's already very significantly different. So basically, it's almost like a different theory. So for sure, you'll get different amplitude.
Yeah, but would be nice, let's say, to classify all the possibilities. Maybe with this approach, with this amplitude approach, one finds just a finite number of extra possibilities that will be nice to classify.
Yeah, that's something we haven't looked at, but it would be something interesting to see.
Okay, thanks.
Okay, there was another question but I don't know the name.
Andre.
Yes. Yes. So do you hear us?
Hello. Hi.
Hi.
Oh, so I wanted to, so you, in the last question, the one before this one, you said that you would expect, if you go to higher orders, that the amplitudes keep being the ones of this scalar tensor theory. Or why would you expect it? Like, so to understand, like, to see if I understood correctly, you proved that these two theories are equivalent at the level of scattering amplitudes for 4-point functions. But why would you expect it if you go to n-point functions?
I get based on the dimensional reduction picture. That's why we expect it to keep holding at higher point. Yeah, just based on the fact that there's also this dimensional reduction picture that's giving us the same. It's giving us all these consistent, different ways of scaling and the theory that we expected. So I guess that's why we expect it to keep happening at higher order.
Okay.
But yeah, maybe you would need to do it to check for sure.
And also about, because you said that the strong coupling problems in some of the examples, they are shoulder on flat backgrounds, but they will be there generally in arbitrary backgrounds, right?
Yeah.
Okay, thank you.
Okay, are there more questions? I do not see any more questions, so I would like to thank you again. Thank you very much.
Thank you for giving the opportunity.